Something in this universe is in two places at the same time right now, and the only reason it picks one is because you looked at it. Not metaphorically, not philosophically, physically. The act of you observing something changes what that something is. And that sentence is not a riddle or a Zen koan. It is the foundation of every computer chip, every laser, every MRI machine, and every smartphone screen on Earth. The technology powering 30% of the entire global economy runs on rules so strange that the man who helped invent them spent the last 30 years of his life insisting they couldn't possibly be true. Welcome to quantum physics. And I promise you, by the end of this, you are going to understand it. Not pretend to understand it the way people nod along at dinner parties. Actually understand it. The real thing, the weird thing, the thing that broke the smartest people who ever lived. Let me start with the world before all of this. Because before quantum mechanics showed up and ruined everyone's afternoon, physics was going great. Sir Isaac Newton gave us gravity and motion in the 1600s. And for about 250 years, those laws worked perfectly. You throw a ball, it arcs through the air, it lands exactly where the math says it will. You have a planet, it orbits the sun, it shows up on schedule. The universe, according to classical physics, was a giant clockwork machine, deterministic, predictable. If you knew the position and speed of every particle in the cosmos, you could calculate every event that would ever happen, forward and backward, for all of eternity. The universe was not mysterious. It was just very large. This is the world scientists lived in until the late 1800s. And honestly, it was a comfortable world. Physics was basically a solved problem. Some scientists at the time were saying the only thing left to do was measure known constants to more decimal places. Wrap things up, close the book, go home. Then someone turned up the heat. I mean that literally. In the 1890s, a German physicist named Max Planck was studying something called black body radiation. A black body is basically a perfect oven, something that absorbs all light and heat, that hits it and then radiates that energy back out. The question Planck was trying to answer was simple. If you heat up an object, what kind of light does it give off, and how much? Classical physics had an equation for this. The problem was the equation was catastrophically wrong. At high frequencies, the ultraviolet end of the spectrum, the classical equation predicted that a hot object should radiate infinite energy. Infinite. Every oven in the world should be exploding with infinite ultraviolet radiation the moment you preheat it to 350 degrees for your Thursday casserole. Physicists call this the ultraviolet catastrophe, which is a deeply dramatic name for a math problem, and also the best band name that nobody has used yet. Planck was not trying to revolutionize physics. He was just trying to fix the equation. And so he did something that at the time he described as a desperate mathematical trick. He assumed that energy was not continuous. He assumed that energy came in tiny, discrete chunks, little packets. He called them quanta, from the Latin word for how much. The math worked. The equation matched the experimental data perfectly. Planck had accidentally invented quantum theory, and he spent the next several years hoping nobody took it seriously, including himself. Albert Einstein took it seriously. In 1905, Einstein used Planck's idea to explain something called the photoelectric effect. When you shine light on a metal surface, electrons get knocked off. Simple enough. But the weird part was this. The number of electrons knocked off didn't depend on how bright the light was. It depended on the color. Dim blue light knocked off more electrons than blazing red light. According to classical wave theory, this made no sense. Light was a wave, and a bigger wave should transfer more energy, full stop. But Einstein said Planck was right. Light wasn't just a wave. It was also made of particles, little packets of energy he called photons. The color of light determined the energy of each photon, and each individual photon had to have enough energy to knock an electron free. A dim blue light with high energy photons would knock off electrons all day. A blinding red floodlight with low energy photons would knock off nothing. Einstein won the Nobel Prize for this in 1921. Not for relativity, which everyone thinks, for the photoelectric effect, for proving that light was made of particles. Here is where things start getting uncomfortable. Because Physicists had proven decades earlier that light was made of waves, the double-slit experiment. Thomas Young, in 1801, took a barrier with two narrow slits cut into it, shone light through it, and looked at the pattern on the wall behind. If light were particles, like bullets from a gun, you would expect two bright stripes on the wall, one behind each slit. Instead, you got an interference pattern. Dozens of alternating bright and dark bands spreading across the wall, the kind of pattern you only get when waves overlap. When the peak of one wave meets the peak of another, they add together and make bright. When a peak meets a trough, they cancel out and make dark. This was irrefutable proof that light was a wave. So, to recap, light is a wave. Light is also particles, both proven, both true, both completely incompatible with each other. The universe apparently did not get the memo that it was supposed to pick one. This is not a metaphor for ambiguity. This is a literal experimental result. You can do the double-slit experiment in a high school lab. You get the interference pattern every single time. Light is somehow both things at once. And the fact that this sentence makes no intuitive sense is not a failure of the explanation. It is the explanation. And then someone asked the obvious follow-up question. If light goes through two slits at the same time like a wave, what actually happens at the slits? Is the photon going through the left slit or the right slit? So they try to find out. They set up a detector at the slits to measure which one each photon went through. The interference pattern disappeared. The moment they measured which slit the photon went through, the photon stopped behaving like waves and started behaving like particles. Two stripes on the wall, no interference pattern. The act of measuring the photon changed what the photon did. Not because the detector physically disturbed it, you can make detectors so gentle they barely interact with the photon at all. It didn't matter. The measurement itself collapsed the wave behavior into particle behavior. The universe, it turns out, does not like being watched, which is extremely relatable. This is the measurement problem, and it has been the most uncomfortable thing in physics for about 100 years. It suggests that the reality of a quantum object, whether it's here or there, whether it went left or right, is not determined until something interacts with it. Before that interaction, it exists in what's called a superposition. All possible states at once. The photon went through both slits simultaneously until we forced it to choose. Niels Bohr, the Danish physicist who became the architect of what we now call the Copenhagen interpretation of quantum mechanics, said this directly. A quantum object does not have a definite position until it is measured. It is not that we don't know which slit it went through. It is that there is no fact of the matter until the measurement happens. This is the part where Albert Einstein entered the room and put his foot down. Einstein had helped start this revolution. But he deeply, personally, philosophically hated where it was going. He spent the better part of 30 years trying to prove Bohr wrong. His objection was simple and human. God does not play dice with the universe. He refused to accept that nature was fundamentally random. He refused to accept that a particle could have no definite position until measured. He believed there had to be hidden variables, some deeper layer of physics, not yet discovered, that would restore the clockwork universe underneath all the quantum strangeness. Reality, Einstein insisted, must be real whether anyone is looking at it or not. This is where our subplot begins, because Einstein did not just grumble privately. He published. In 1935, Einstein, along with two colleagues named Boris Podolsky and Nathan Rosen, wrote a paper that laid out what seemed like a devastating logical trap for quantum mechanics. The paper introduced a scenario that later became famous as the EPR Paradox, named after their initials. And the scenario went like this. Take two particles and allow them to interact in a way that links their quantum states, what physicists call entanglement. Now, separate them. Move one particle to one side of the lab and the other particle to the other side of the lab. Or, for dramatic effect, to opposite ends of the galaxy. Now measure one of them. The moment you do, quantum mechanics says you instantly know the state of the other one, no matter how far apart they are. If one particle spins up, the other spins down, instantaneously, without any signal passing between them. Einstein said this was absurd. Either quantum mechanics was incomplete and there were hidden variables deciding the outcomes in advance, or measuring one particle was somehow sending information to the other one faster than light, which relativity said was impossible. He called it spooky action at a distance, mostly as an insult. He meant it to sound ridiculous. He thought he had cornered Bohr. Bohr responded that the two particles don't have separate definite states until one is measured. They are one system. There is no signal being sent. The correlation is real, but non-local. Which, let's be honest, sounds even more ridiculous. Two physicists, both geniuses, both talking to each other in riddles, and the rest of the physics community slowly backing away toward the exits. For the next few decades, the EPR debate was mostly philosophical. Neither side could prove the other wrong experimentally. Einstein died in 1955, still convinced that quantum mechanics was incomplete. Bohr died in 1962, presumably content, and the argument appeared to be headed toward the dustbin of history. Then, in 1964, a physicist named John Bell did something extraordinary. He proved that the question was not philosophical at all. Bell derived a mathematical inequality, a set of limits that any hidden variable theory would have to satisfy. If Einstein was right, and particles had predetermined hidden states all along, then measurements of entangled particles would correlate in ways that stayed within Bell's limits. If quantum mechanics was right, if the particles genuinely had no definite states until measured, then the correlations would violate Bell's inequality. The two possibilities produced different, measurable, testable predictions. Bell had turned a metaphysical debate into a physics experiment. This is the part that changes everything. Stay with me. In 1982, a French physicist named Alain Aspect performed the test. He created pairs of entangled photons, separated them, measured them, and calculated the correlations. The results violated Bell's inequality, not slightly, decisively. The universe does not have hidden variables. Einstein was wrong. Particles genuinely do not have definite states before measurement. Bohr was right. The quantum world is fundamentally, irreducibly random. Reality does not exist until observed. Aspect later received the Nobel Prize in Physics in 2022 for this experiment, which is the kind of 40-year gap between discovery and recognition that makes you wonder what else the prize committee is sitting on. The man who spent 30 years insisting the universe was deterministic had lost, not to a philosophical argument, to an experiment with lasers and math. And yet, here is the thing, and this is the part nobody talks about enough. Einstein's discomfort wasn't stupid. His intuitions weren't crazy. His insistence that something deeper must be going on was, in many ways, the healthiest scientific response to a theory that seemed to violate every sensible notion of reality. He was wrong about the conclusion. He was not wrong to demand an explanation, because quantum mechanics, even today, has a problem. It works. It works better than any theory in the history of science. It predicts experimental results to 10 decimal places. It explains the structure of every atom in existence. It is the most precisely verified theory ever produced by human minds. But it does not explain why. It does not tell you what is really happening when a particle is in superposition. It does not tell you what observation really means, or why measurement collapses a quantum state, or what reality is between measurements. Schrödinger's cat is the famous illustration of this problem. Erwin Schrödinger, who was brilliant, prickly, and not a cat person, as far as anyone can tell, proposed a thought experiment in 1935, the same year as the EPR paper. Imagine a cat in a sealed box. Inside the box is a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers, the vial breaks, the cat dies. If the atom doesn't decay, the cat lives. Quantum mechanics says the atom is in superposition decayed and not decayed simultaneously until something measures it. But the atom is connected to the cat. So before you open the box, is the cat both alive and dead at the same time? Schrödinger's point was not that the cat is actually in superposition. His point was that the Copenhagen interpretation, taken seriously, produces this absurd result. The bridge between the quantum world of atoms and the classical world of cats and boxes and people is not explained by the theory. The theory just says, before measurement, superposition. After measurement, one definite outcome. It doesn't say what measurement is, or when it happens, or what counts as an observer. Is a camera an observer? Is a thermometer? Is an atom hitting another atom? The theory doesn't say. The theory just works. And this is where the deepest strangeness of quantum mechanics lives. Not in the weirdness of the experiments, but in the gap between the math and the reality. The math is perfect. The reality behind the math is completely opaque. There are, at last count, at least a dozen competing interpretations of quantum mechanics. The Copenhagen interpretation, which says, don't ask about reality between measurements, just calculate. The many worlds interpretation, proposed by Hugh Everett in 1957, which says every time a quantum event resolves, the universe splits into branches. In one branch, the cat is alive. In another, it is dead. Both branches are equally real. There are now an incomprehensibly large number of parallel universes branching off every microsecond for every quantum event in every atom in existence, which is either beautiful or deeply exhausting depending on your mood. There is the pilot wave theory, which tries to restore determinism by having particles guided by a hidden wave. There is the relational interpretation, which says quantum states are always relative to some observer. There is cubism, which says quantum states are just an agent's beliefs about measurement outcomes. None of these interpretations changes the experimental predictions. They all give the same numbers. They are all equally successful as physics. They are completely different pictures of what reality is. And there is currently no experiment that can distinguish between them. What this means is the following. We have built the most successful scientific theory in human history. We have used it to invent transistors, lasers, atomic clocks, MRI machines, and the entire semiconductor industry. We are currently building quantum computers that exploit superposition to perform calculations that classical computers could not finish before the sun expands into a red giant and swallows the earth. And we have absolutely no consensus on what any of it means. This would be alarming if it weren't also kind of hilarious. Richard Feynman, who won the Nobel Prize for his work on quantum electrodynamics, the quantum theory of light and matter, and who was the kind of person who figured out complex physics while playing bongos at a strip club in Pasadena, said something that became the most honest sentence in science. He said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." He wasn't being modest. He was describing the actual situation. The theory works. The reality it describes is not comprehensible in human terms. Our brains evolved to navigate a world of rocks, predators, and fruit. Our intuitions were calibrated for the scale of things we can hold in our hands. The quantum world operates at scales 100,000 times smaller than the width of a human hair. And at those scales, the universe plays by rules that have no analog in everyday experience. There's no better analogy for quantum superposition because nothing at human scale is ever in superposition. The best we can do is describe the math and say, this is how it behaves, and the math is correct. And don't ask what it means when nobody is looking. Here's something that should make you stop and sit for a second. Every atom in your body has electrons. Those electrons exist in quantum states described by probability distributions, clouds of likelihood, rather than fixed orbits. The reason your hand doesn't pass through the table when you press them together is not because your atoms are solid. They are mostly empty space. It is because of a quantum rule called the Pauli exclusion principle, which says that no two electrons can occupy the same quantum state in the same place at the same time. The solidity of everything you have ever touched, every chair, every wall, every handshake, every sidewalk, is a consequence of quantum mechanics. The hardness of the physical world is quantum. Without it, matter would collapse into itself, and the entire universe would be a soup of undifferentiated particles with no structure at all. The color of gold is quantum. Gold should be silvery, like most metals. But gold atoms are heavy enough that Einstein's special relativity causes the innermost electrons to move at a meaningful fraction of the speed of light, which shifts their energy levels, which changes how they absorb and reflect light. The yellowness of gold is a relativistic quantum effect. Your wedding ring is a physics lecture you wear on your finger. The reason the sun shines is quantum. The sun fuses hydrogen atoms into helium, but classically this should be impossible. The protons at the core of the sun don't have enough energy to overcome the electrostatic repulsion between them and actually touch. They can't get close enough to fuse, but they do fuse. Every second, the sun outputs 3.8 times 10 to the 26th watts of energy, which is a number so large it barely counts as a number. The reason it can do this is quantum tunneling, the ability of quantum particles to pass through energy barriers that classical physics says are impenetrable. The protons don't go over the barrier, they tunnel through it, literally. The light warming your face right now exists because particles phase through walls. And now, coming back to entanglement, because this is the part that is about to reshape human civilization in ways that aren't yet fully legible. And I think about this a lot. Quantum entanglement is not just a curiosity, it is a resource. When two particles are entangled, measuring one instantly determines the correlated property of the other, regardless of distance. You cannot use this to send information faster than light. And this is a subtle and important point that trips people up constantly because the outcome of each measurement is random. You can't control what result you get, so you can't encode a message in it. But you can use the correlations to build something called quantum cryptography. Two parties share entangled particles. They measure them and use the correlated results as an encryption key. The key is truly random, generated by quantum probability. And crucially, any eavesdropper who tries to intercept and measure the particles will disturb the quantum states, and that disturbance is detectable. A quantum encrypted message is the first information system in history where eavesdropping is physically impossible without leaving evidence. Every spy, every intelligence agency, every corporation that has spent decades building ways to intercept encrypted data is about to face a communication system they literally cannot crack by the laws of physics. Not by convention, by law. Nature's law. Quantum computers are the other frontier. A classical computer bit is either 0 or 1. A quantum bit, a qubit, can be in a superposition of 0 and 1 simultaneously. 2 qubits can be in a superposition of 4 states at once. 3 qubits, 8 states. 10 qubits, 1,024 states. 50 qubits, over 1 quadrillion states simultaneously. A quantum computer doesn't just run faster, it runs differently. For certain categories of problems factoring large numbers, simulating molecular chemistry, optimizing enormous logistical systems, it can find solutions in minutes that would take a classical computer longer than the age of the universe. IBM has a quantum processor with over 1,000 qubits as of recently. Google claimed quantum supremacy in 2019 when their processor performed a specific calculation in 200 seconds that they said would take a classical supercomputer 10,000 years. IBM pushed back on that number. The debate about the exact speedup continues, but nobody is debating whether quantum computers are real or whether they are coming. They are here. They are being built. They are getting better every year. The banks know this. The militaries know this. The intelligence agencies absolutely know this. Current encryption standards, RSA encryption, which secures most of the internet's sensitive data, rely on the mathematical difficulty of factoring large numbers. A sufficiently powerful quantum computer running an algorithm called Shor's algorithm could break RSA encryption in hours. Every bank transfer, every private message, every classified document secured by modern encryption is potentially vulnerable to a quantum attack the moment quantum computers reach sufficient scale. Governments are already transitioning to post-quantum cryptographic standards. The National Institute of Standards and Technology in the United States finalized its first set of post-quantum cryptography standards in 2024. The race is not theoretical. The clock is ticking. And here is where I want to bring Einstein back. Because Einstein, who spent his last decades being the stubborn old man who refused to accept quantum mechanics, who insisted the universe must be deterministic, who called entanglement spooky action at a distance, as a term of derision that man's work on special relativity is why gold is yellow. His general relativity is in the GPS satellites that your phone uses to navigate. His photoelectric effect paper is literally the start of the quantum revolution he later despised. He is woven into all of it, for and against, foundational and resistant, right and wrong simultaneously in ways that are, you might say, almost quantum. The man existed in superposition, determined and open, convinced and curious, a particle and a wave. And maybe that is the thing about quantum physics that is hardest to sit with and most worth sitting with. The theory does not tell us what reality is. It tells us what reality does. It gives us perfect predictions about outcomes and complete silence about the nature of the underlying truth. Every interpretation we have tried, Copenhagen, many worlds, hidden variables, relational, informational, is a story we are telling ourselves to make peace with equations that work without needing us to understand them. The universe is not structured to be comprehensible to humans. It is structured to be what it is. We are the ones who arrived late, looked around, and assumed we were owed an explanation. We were not. What we were given instead was the ability to use the strangeness, to build with the weirdness, to exploit the superposition, the tunneling, the entanglement, the measurement effect, not by understanding what they mean at the deepest level, but by learning the rules well enough to do something with them. The transistor was invented in 1947. There are now more transistors on Earth than there are leaves on all the trees in the world. Every one of them is a quantum device. Quantum mechanics didn't just explain nature. It gave us the tools to build a new one. Erwin Schrödinger put a cat in a box to mock the Copenhagen interpretation. Somewhere in a quantum computing lab right now, engineers are putting qubits into superposition on purpose, industrially, at scale, because the cat being both alive and dead at the same time is useful. It turns out the absurdity was always the point. In the beginning of this, I told you that something in the universe is in two places at the same time, and the only reason it picks one is because you looked at it. That sentence probably sounded like a trick, like something designed to sound deep without meaning anything. But by now you know it is not a trick. It is the result of a century of experiments, starting with a man trying to fix an equation about ovens, passing through a battle between two of the greatest minds in history, landing in a French laboratory in 1982, where a man with lasers proved that Einstein's most stubborn conviction was wrong. The universe is not a clockwork machine with hidden gears. It is something stranger and more open. It decides things only when forced to. It holds possibilities open until the last moment. It is, in some fundamental sense, made of potential rather than fact. Einstein lost the argument, but he asked the right question. And maybe that is the real lesson of quantum mechanics, not the weirdness of the answers, but the audacity of continuing to ask. The cat was always both.